I want to make a few comments about the change of variable business that are different from the specific coordinate systems that we've dealt with previously, which in 2 dimensions were Cartesian versus polar, and in 3 dimensions, Cartesian, cylindrical, and spherical. Instead, I want to think about changing variables in a way that's going to make integration problems easier to do. So I'd like to find the double integral over region R of 6 times x times y integrated with respect to area, but my region R is described in kind of an odd way. It's bounded by different curves, or lines in this case. Y equals 6 minus 2x and y equal 8 minus 2x form part of my boundary. Part of it is y equal x and y equal x plus 1. The diamond-shaped region in the middle is what I'm going to call R. If I wanted to do this in Cartesian coordinates, I'd have to split the region up into at least 2 smaller regions because what constitutes the top function changes at the intersection point of this straight line and y equal x plus 1. Depending on how it's oriented, I might have to break it up into as many as 3 double integrals to do, which is obviously undesirable. The way around this problem is to take advantage of the difficulty. If you look at y equals 6 minus 2x and y equal 8 minus 2x, you can rewrite those facts as 2x plus y equals 6 and 2x plus y equal 8. The quantity 2x plus y will vary between 6 and 8 for points in the region. Also, y equal x plus 1 can be written as y minus x equals 0 and y minus x equals 1. If you look at all of the points where 2x plus y is between 6 and 8, and y minus x is between 0 and 2, those will give you all the points in the region. So it seems reasonable to change variables. We're going to let u equal 2x plus y, and we're going to let v be y minus x. The points that go with region R are going to be the points where u is between 6 and 8, and v are between 0 and 1. This is a much easier description of the region. Of course, now we've got a couple of issues to deal with. For one thing, I'm integrating something and it's expressed in terms of x and y. I have to express x and y in terms of u and v if I want to do the integral, but also we need to know that j factor. So we're going to need to know x and y as functions of u and v. If I take the fact that u is 2x plus y and v is y minus x, if I subtract those two equations, if I look at u minus v, when everything is done, that turns out to be 3 times x. That means x is 1/3 u minus 1/3 v. This second equation says that v is y minus x. That means that y must be x plus v. And we've already established that x is 1/3 u minus 1/3 v. So putting that fact in and simplifying it, I find out that y is 1/3 u plus 2/3 v. So we now know x and y in terms of variables u and v. If we form the matrix of partial derivatives of old coordinates with respect to new ones, It's direct to see in this case that the partial derivatives are one third, negative one third, and two thirds. If you do the determinant of that, it turns out to be 2/9. The factor that I have to put in that's similar to the r factor in polar coordinates is a constant. It's 2/9. So we're now going to integrate from 6 to 8 with respect to u, integrate from 0 to 1 with respect to v. There's my j factor, and I'm wanting to integrate 6xy. I can pull a factor of 6 and a factor of 2/9 out front, giving me 4/3 integral from 6 to 8 with respect to x of the integral from 0 to 1 with respect to v of x times y. My remaining difficulty is I have to express x times y in terms of u and v, but I have formulas for x and for y separately in terms of u and v, so that really shouldn't be a big problem. If I use the formulas that I figured out for x and y in terms of u and v, it's just a bit of algebra to see that x times y has to be 1/9, there's another constant factor, times u squared plus uv minus 2v squared. Pulling the constant factor out in front of the integral, as usual, I found out that I have to calculate 4/27 times the integral from 6 to 8 with respect to u, integral from 0 to 1 with respect to v of u squared plus uv minus 2v squared. And see, everything is nice now. I just have to integrate polynomials and I'll have my answer. Doing the inside integral first. Remember, v can't show up in the answer because it's a definite integral, but u can. Take an antiderivative with respect to v, evaluate it at v equals 1 and v equals 0, and subtract, and we get for our inside integral u squared plus 1/2 u minus 2/3. So to finish our problem, we have to calculate 4/27 times the integral from 6 to 8 of u squared plus 1/2 u minus 2/3 with respect to u. An antiderivative is 1/3 u cubed plus 1/2 times 1/2 u squared, that'll be 1/4 u squared, minus 2/3 times u. I put these numbers, 8 and 6, into the antiderivative. I did this with my calculator, multiplied the result by 4/27. The integral that we're after is 15.45679 to a few decimal places. Another example of this, I'm going to think about having a region that's bounded on two sides by straight lines and on the other two sides by hyperbolas. I'm going to have y equal 1 over x, which is a hyperbola, y equal 4 over x, which is a higher up hyperbola. I'm going to think about having the straight line y equal x over 2 and the straight line y equal x. The region bounded by these four graphs I'm going to call R, and I'd like to figure out some reasonable way of describing R so that I could do double integrals over it if I wanted to. Part of my boundary is formed by y equal x over 2. Part of it's formed by y equal x. For a given x number, every point in my region is going to be between x over 2 and x. If I form the quantity y divided by x, that will vary from 1/2 to 1. So obviously, I'm going to name one of my variables. I'm going to make it equal to y over x. On the other hand, if you think about the hyperbolic part, y could be as small as 1 over x or as big as 4 over x. That says that x times y has to be between 1 and 4. So my new variables are going to be y over x and x times y. We'll make up actual names for them in a moment. In the meantime, I want to start thinking about my actual integral. I want to find the double integral over the indicated region of x times y integrated with respect to area in the xy plane. I'm going to I'm going to let u equal y divided by x and v equal x times y. Region R then is described by 1/2 less than or equal to u less than or equal to 1 less than or equal to v less than or equal to 4. The description of the region is now very simple in terms of these new variables. In fact, x times y is the thing that I'm integrating. So actually, I'm just integrating the v coordinate. I want to find the integral from 1/2 to 1 with respect to u of the integral from 1 to 4 with respect to v of v. But then I have another problem. I have to put in that j factor. This was the absolute value of the determinant of the old coordinates with respect to the new one. Unless I want to do some linear algebra trickery, I've got to figure out formulas for x and y in terms of u and v so that I can calculate these 4 partial derivatives I need and then get the j number. So what follows is just a little bit of algebra. U is by definition y over x here, and v is x times y. I'm looking at those two equations and I'm trying to think of how to get either x or y by itself. After looking at it just a little bit, you have an epiphany. U times v is y over x times x over y. The x's cancel out. U times v is y squared. Since our region is in the first quadrant, both x and y are not negative, so I don't have to worry about the whole plus or minus thing. Y has to be the principal square root of u times v. On the other hand, we've got this formula that says x is v divided by y, so write that down. We have just found out that y is principal square root of u times v. V, since it's non-negative, is the square root of v squared. Combine those into one square root, cancel out a factor of v, and you'll find out that x is principal square root of v divided by u. So we now have x and y in terms of u and v. In the algebra and the partial derivatives that follow, I found that it was more convenient to write these things as powers. So this is v to the 1/2 power as a factor. I have 1 over u to the 1/2. So that's u to the negative 1/2 v to the 1/2. Y equals radical uv. That's the product of radical u times radical v, which I will write as powers also. In the rest of it, you're just using the ordinary power rule for derivatives, so you can look that over if you like. After you've got all of the derivatives, I have to calculate this one times that one minus that one times that one. That's how we get the J number. Write down all of those factors. The determinant works out to be negative 1/4 times 1 over u plus 1 over v. U and v are both positive, so I need to take the absolute value of that to get 1/4 times 1 over u plus 1 over v. This turns our integral, double integral over region R of v with respect to area, it turns it into the integral from 1/2 to 1 with respect to u, the integral from 1 to 4 with respect to v of the thing that we're integrating, which was v, times the j factor. Multiplying the v through, I've got 1/4 times the integral of v over u plus 1. The inside integral is not very hard to get then. Remember, in the inside integral, we're going to treat v as though it's the variable and u as though it's a constant. An antiderivative for v over u would be v squared over 2u. An antiderivative for the constant 1 is v. Put v equal 1 and v equal 4 in and subtract them. And at the end, you end up with 15 divided by 2 times u plus 3. This is the integral with respect to v. We don't want to see any v in it, but it's okay that the u still shows up. All that remains is to calculate the integral from 1/2 to 1 with respect to u of the constant 15/2 times 1 over u plus the constant 3, which is an easy integral to do. The antiderivative is 15/2 natural log of u plus 3u. Put u equal 1/2 and u equal 1 in. Grind through the arithmetic. I made use of the fact that natural log of 1 over 2 is the negative of natural log of 2 here. And if you want your answer in exact form, this would be what you would have. I guess you could take another factor of 1/2 out if you thought it looked nicer. These techniques where you have a double integral and there's some fairly obvious connections between bounds on the region, this technique is occasionally good to know. Occasionally it comes in handy. I've decided not to make a big production number out of it because we have other things to think about. Hopefully our technology will all be working soon. I'll talk to you again.